Hello everyone! Good morning, good afternoon, and good evening, and welcome to another RTDS Technologies webinar. My name is Katie Sidwall. I'm on the technical marketing team at RTDS, and I'm joined by my colleague Eric Xu, who will be doing today's presentation and demo. Today we're looking at modeling protection and control for IEEE 1547 standard compliant DER interconnection. I'll begin by speaking for 10 minutes or so to give some background on DER studies with the RTDS Simulator for people who might not be familiar, and then get into some details about the case we're looking at today, as well as some new developments in this area. Then Eric will take over, and for about 30 minutes total, he'll go through a presentation on IEEE 1547 and our case today, and then he will do a screen share demonstration of running the RSCAD case. Once that's done, we will go into our live Q&A session. So please start thinking of your questions. You can use the Q&A widget to submit them. You should be able to see it near the top left corner of your webinar platform. So throughout the programming today, please submit as many questions as you like, and we will be here to answer them throughout the content, and then we'll select a few to discuss in more detail at the end of the webinar. This webinar is being recorded and distributed afterward, so no need to worry about that. Anyone who's attending today can revisit this webinar, can watch it on demand. You can share it with your colleagues who might have missed it today, so they can watch it on their own time as well. And the slides from today's presentations are available for download right now in the additional materials section. So it should be close to the bottom left-hand corner of your webinar platform. You can download a PDF of today's slides and follow along or share. Finally, if you have any audio-video issues, feel free to drop us a message in the chat. Also, feel free to say hello, introduce yourself, let us know where you're joining us from. It's great to have a global audience, as always. All right, so let's get started here. If you're not familiar with RTDS Technologies, we are headquartered in Winnipeg, Manitoba, Canada. We pioneered real-time power system simulation in the 1980s. Today, the RTDS Simulator is the industry standard for real-time simulation and closed-loop or hardware-in-the-loop testing, used by utilities, manufacturers, research and educational institutions, and consultants. We won't be giving too much of a primer on the technology today, so if you want to learn more or you're curious about other applications of real-time simulation, please visit our website at rtds.com or check out our YouTube channel. We have a large library of webinars and other educational videos that you can check out. The RTDS Simulator does electromagnetic transient, or EMT, simulation of power systems. And EMT simulation is more detailed than traditional methods of modeling the power system. Load flow and transient stability analysis, for example, give phasors around the fundamental frequency, and they offer a positive sequence-only representation of the power system, limited to balanced system phenomena. EMT simulation provides a time-varying instantaneous value output. So the simulation output ideally gives you a waveform that matches the current or voltage if it were measured from the real system. And this allows for a greater depth of analysis over a wide frequency range and the ability to reproduce fast transients on the power system. The typical time step, or distance between consecutive outputs, is 25 to 50 microseconds, but much smaller time steps are possible as well for certain applications, such as power electronics simulation. The greater depth of analysis provided by EMT simulation is especially important in the modern power system, where we have a high penetration of inverter-based resources. EMT models can capture the transient behavior of these power electronic converters and can also model their fast-acting low-level control, which ends up being a significant contributor to the overall behavior of the grid and a point of vulnerability as well. In the images on this slide comparing the results of RMS and EMT simulations, the EMT simulations are capturing some dynamic behaviors that are not visible using traditional simulation. And being able to capture those deviations is very key for identifying and mitigating vulnerabilities in the DER-heavy modern grid. Running our simulation in real time is what separates the RTDS Simulator from other offline EMT programs such as PSCAD. When we say real-time, we mean the computer needs to solve all of the equations for the network in real-world time equal to or less than the simulation time step. This means that the real time required for a power system event to occur is equal to the time required for the RTDS simulator to represent it. The main advantage of running simulations in real time is the ability to connect external hardware to the simulation and test it in a closed loop. That's what we call hardware in the loop testing. And closing the loop means not only observing the response of a protection or control device to an imposed signal, but also interfacing that response back into the simulated network. Hardware in the loop testing is only possible if we're updating the inputs and outputs of our simulation continuously in real time. And with hardware in the loop testing, we can test multiple devices at once. Entire coordinated schemes can be tested simultaneously. We can represent nearby resources like power electronics in great detail. So there's a lot of flexibility and detail provided. Today we're talking about DER interconnection. And DERs are a huge application area for us, particularly when it comes to inverter-based resources. So I thought I'd give you an idea of the other types of projects that are happening in the renewables and DERs space. DER integration studies can be small or large scale, and typically these are done by utilities or system operators. We have users looking at how large planned quantities of renewables will affect the strength, the inertia of the grid, and potentially interact with other technologies. In Australia, for example, where they have massive quantities of DERs that will be added alongside a new HVDC link. Or looking more at a single plant installation like we're doing today. Utilities are requiring vendors to provide an accurate EMT model of their DER controls in order to validate the performance of the DER and de-risk the interconnection to their grid. And that's more and more key as DER controls become wider in scope and functionality and in complexity. An important aspect here is the ability for those vendors to provide the EMT models in a way that protects their intellectual property. So offline tools like PSCAD have established methods for doing this, but it's a little more difficult when that protected black box control model needs to run deterministically in real time alongside the simulation. We have a new solution for this, and I'll show you that in a moment. We also have users looking at how DERs impact existing protection on the grid. The photo here is from Quanta Technology, a consultant in the US, who recently did a project where they tested protection on a 345 kV line tied to a wind farm facility. And we have another webinar available where you can learn the gaps and interactions that they identified. Grid forming control testing. We've had research institutions validating novel GFC algorithms through HIL testing, and you'll see some GFC functionality in today's case. Inverter testing. The testing of physical inverters at a wide range of power levels is also possible via power hardware in the loop testing. So here you're using a 4-quadrant amplifier to connect an inverter and a solar panel, for example, or a controllable DC source, to the real-time simulation to determine its response to various events and conditions on the grid. So testing not just on the control level for DERs, but also at the power device level. Power plant controller, or PPC testing. A major justification here is model validation. So if a vendor wants to ensure that the PSCAD model they provide to the customer is accurate, they can benchmark it against the performance of the actual PPC hardware connected to the simulated utility grid. And finally, we have replica testing. This is established in the HVDC and FACTS space, where the system operator receives a replica of the HVDC control cubicles, and they live in a lab connected to a real-time simulator which models the utility grid. We're seeing this starting to come up for large DER plants as well, where a lab-housed replica of the controls allow the utility to speed up the commissioning process, conduct tests that aren't convenient or possible in the field, troubleshoot, and de-risk any changes through the project lifetime, for example, for a large battery energy storage system. So this is the GT SOC. This is the recent development at RTDS for the black box control modeling that I mentioned. It's a rack-mounted unit that can be added to the RTDS Simulator. It features a powerful FPGA board with multiprocessor system-on-a-chip technology. So the ARM cores on this board allow for vendor controls to run in real time as part of the real-time simulation, while remaining black-boxed, protecting vendor IP. The GTSoC runs static.a library files, which contain the controller source code, whereas offline tools like PSCAD would use DLL files, which the audience might be familiar with. So if you're interested in the GTSoC or you have any questions, please contact RTDS and we'd be happy to share more about this with you. We're currently developing a webinar on this new technology, which we will be having before the end of the year, so you can look forward to that as well. Okay, a couple things about today's case before I pass it off to Eric. What you'll see today is a sample case available in RSCAD FX version 1.2 and newer. So if you're an existing customer with up-to-date RSCAD, you can access it today, and it compiles on a single core, all in the main step environment. So anyone with Nova Core can run this case. The protection and control is modeled in RSCAD. Eric will show you how he's built out the controls using our protection and automation and controls component libraries. But the whole idea is that the control could also be external to the simulation and connected via I/O for hardware in the loop testing. Also, the converter in the case is modeled using our new universal converter model, the 2-level flavor. So I wanted to touch on that really briefly. The UCM is available for a variety of converter topologies, and it can be placed in either of the major time step environments. The main step environment at a typical 25 to 50 microseconds, or the sub-step running at a fraction of the main time step between 1 and 10 microseconds. The performance and the processing weight of this model are determined by not only the simulation environment, but also the input type, and there's a couple different options there. The most relevant are the modulation wave input and the improved firing input. Modulation wave input is essentially an average value model of the converter. It doesn't represent detailed switching, so it's applicable for studies where you're interested in the higher level controls and the real and reactive power profile of the converter is sufficient. Improved firing is a proprietary algorithm which simulates detailed switching with no artificial losses and no decoupling at the DC bus at higher switching frequencies than were possible previously. In the substep environment, the model allows switching in the 150 kilohertz range, and what's really groundbreaking is that it can be placed in the main step environment with this input to represent detailed switching up to 10 kilohertz. And in the main step environment, the detailed switching version of the model takes up only 10 load units, the same quantity of load units that would be used for the modulation wave version. So if you're familiar with the RTDS Simulator hardware allocation, you know that's a very lean model. It means that folks working with just a single licensed core can place several converter models switching up to 10 kilohertz and model or test their low-level firing pulse control that way. All right, thank you so much everyone for your attention. I will now pass it off to Eric, and you'll be in his hands for the presentation and demo. And I'll see you in the live Q&A.
Thanks, Katie, for the introduction. I'm Eric Xu from RTDS Technologies. The topic today is on modeling protection and control for IEEE 1547 compliant DER interconnection. In this webinar, we will start with a brief introduction to the IEEE 1547 2018 standard, followed by a detailed look of modeling of the protection and control of DR-grade interconnection based on some of the key criteria specified in the standard. Then we will run the simulation, followed by the Q&A session at the last. IEEE 1547 is the standard for interconnection and interoperability of DRs with associated grade. It addresses standard technical requirements for DR interconnection by providing uniform criteria and requirements relevant to the performance, operation, and testing of the interconnection. Key criteria covered in the standard include synchronization of the DER to the grid, response to the grid abnormal conditions, such as undervoltage, overvoltage, voltage disturbance right through, and similar criteria for frequency related. Here shows the diagram of the power system network modeled in this case. The DER here represents a simple battery system modeled by a DC source. It's interfaced with the grid using a converter through the point of common coupling PCC here. The connection point here, where the DER is directly connected to, is often referred as point of DER connection, POC. The DER runs on grid following mode when connected to the grid, and runs on grid forming mode with droop control when isolated. Here shows the simulation modeling. The universal two-level converter model configured to receive modulation waveforms as inputs is used as the DC-AC converter here. The controls of the converter for both grid following mode and forming mode are included in this hierarchy box. Here just highlights the droop control topology of the GFC mode. The protection and control modeling related to the DR grid interconnection are in these two hierarchy boxes. The grid is modeled by the infinite source component, which is configured to have controllable input waveforms for validating the protection and controls. The control for the input waveforms is in this hierarchy box. Next, let's look into the details of the modeling by starting with the synchronization. The synchronization parameter limits shown here, taken from the standard, is applied in this case. The voltage at the PCC and POC bus are compared using the synchrocheck function available in the breaker control component. The parameters are entered in the corresponding fields of the component highlighted here. The breaker advanced close feature is enabled in the component to ensure a smoother transition by closing the breaker at exact zero slip. The final trip and reclose signals are given to the inputs of the component, and the output from the component controls the DR breaker at the POC. A small frequency offset is added to the GFC droop control to speed up the synchronization process. In this case, an offset of 0.0005 per unit corresponding to 0.03 Hz is added to the reference point. A simple reclosing function is implemented, as shown here, which includes auto and manual reclose functions. Now, here shows the DR response to abnormal voltages and its read-through requirement for one of the DR categories specified in the standard. It shows that the DR shall cease to energize or be tripped when the voltage is greater than 1.2 per unit or less than 0.5 per unit, with the maximum response time of 0.16 seconds. For other levels in between, read-through shall be permitted with the minimum read-through time specified in the third column here. The protection and control developed for the voltage disturbances is shown here. The RM has voltages of each phase at the PCC are measured in per unit to detect the maximum and the minimum values, which are then used to compare with the thresholds for tripping conditions. The purple color hierarchy boxes contain the protection and control for consecutive voltage disturbances. In situations when a consecutive disturbance occurs, a disturbance set is established if the time between the two consecutive disturbances is within the specified threshold. The standard specifies that for each DR category, the maximum number of disturbance sets shall be permitted within the specified time window before a trip shall be asserted. The DR shall also be tripped if the accumulated time duration of the consecutive disturbances in the set is over the specified threshold. Here shows developed functions to realize the aforementioned requirement. The limits are adjusted, as highlighted here, for convenient demonstrations in runtime simulation. The modeling for frequency disturbance is similar to the development for the voltage, with some variations such as the requirement on rate of change of frequency, ROCOF, and V over F for a specific frequency range. Here shows the developed function to realize the aforementioned requirement. The PMU component is used here to extract the rate of change of frequency parameter, and also here is the V over F check. The final trip function shown here combines the protections for the voltage and the frequency. This part is to create three-phase sinusoidal waveforms for the source component for validating the developed protection and control functions. So with all that, let's see how it really works in the simulation. Here is the draft we mentioned in early slides. Let's compile it first, then we go to runtime. The first scenario is the synchronization process. The preconditions for this scenario are the gray breaker is closed, the auto reclosing switch for the DR breaker is set off. Then let's start the simulation. The grid will provide power to the load initially. After the startup delay of 5 seconds, the DR bus voltage reaches to the rated value. The DR breaker BRK1 here is still in open state. A vector display compares the phasors of the PCC and the POC bus. The frequency at each of the bus, the slip frequency, the reference frequency in per unit, and the slip time to 0 degrees are all monitored here. Let's start the synchronization process by manually triggering the push button here. The plots will be automatically updated once the DR breaker is closed. Notice that the added frequency offset to the DR juke control accelerates the synchronization process. The DR breaker is closed at 0 sleep as expected. During the transition period, the step change in the RMS voltage at the PCC bus is below 5% of nominal voltage, which satisfies the requirement. The second scenario is on low voltage write-through. Let's switch on the auto reclose. Let's apply an A-phase to ground fault with fault duration of 0.89 seconds. The breaker is remain closed in this scenario. During the fault, the minimum required time for write-through is monitored down here, which have been greater than the duration in which the voltage was within the specified region. (0.88325). Here we have the 0.896. So the DR route through this voltage disturbance as expected with no trip asserted. Next, let's change the fault duration to 1.0 second and redo the test. Let's do update plot first. And then we can reapply this A to ground fault with fault duration of 1.0 second. Now this time the breaker was opened. This time the duration in which the voltage resided in the specified region was greater than the minimum time requirement for write-through. Therefore, a trip was asserted. We can see here this is 0.8961, 0.8960. That's the threshold. So when that happens, the trip was asserted. Okay. And after the drop-off delay, the breaker was opened and the reclosing sequence was initiated as expected here. The next scenario is on consecutive voltage disturbances in a set. Let's do a plot update first. And we'll set the disturbance to 1, and that's the enable for the disturbance, and we're going to apply that disturbance by pressing this button here. Okay. So the controllable source generates a series of voltage disturbances. Each of them has a duration less than the required minimum write-through time. The duration among any two consecutive disturbances is made less than the required minimum time between successive disturbance sets. We can observe from the result that once the accumulated time of the two consecutive disturbances, which are in one disturbance site, reached 0.1 second, which is the set limit, a trip was asserted. We can see the DR breaker was opened and then the auto reclosing sequence was initiated as expected. Let's move on to the next scenario. A consecutive voltage disturbance that are over the set limit. Let's update the plots first. Let's triggering the event by setting the disturbance to the second scenario, and then we're going to trigger this push button here. The controllable source this time generates a series of voltage disturbances. Each of them has a duration less than the required minimum write-through time. The duration between two consecutive disturbances is made to greater than the required minimum time between successive disturbance sets, which is set to 0.2 seconds. It shows that from the simulation result that the first disturbance lasted for around 0.06 seconds. Now the second disturbance occurred over 0.2 seconds later, so that one was considered as the second disturbance set. The time monitoring the consecutive duration is reset here. The third disturbance came in before the time window for new sets expires. Therefore, a trip was asserted accordingly, followed by the auto reclose sequence as expected. Okay. Okay, next let's have a look on the frequency part. Firstly, let's reset some of the parameters here. Disable the voltage disturbance functions here, and then we go to the case options, change the finish time to a little bit longer, 4 seconds. Okay. And then we open the frequency function tabs here. Let's set the direction of the change to increment by setting the switch here to 1, and then we set the slope of the change to 0.49 Hertz per second, and set the maximum frequency to 61.201, which is slightly above the threshold, which is 61.2 Hertz. Now trigger the event by pressing this push button here. We can see the breaker was opened and the reclose was initiated here. Okay. The trip here was asserted after the minimum write-through time expires, which is 0.3 seconds in this case. Now, if we set the slider, the maximum frequency here, to a value below the threshold, let's say 61.19, let's see what happens. Okay, so the breaker is closed again. Let's trigger the disturbance again. Now, in this case, we can see the breaker was remained closed. There's no trip asserted, and the frequency disturbance roll through was written through here, okay, which is expected. Now let's reset the frequency here, and we'll see the breaker will be operated because of the rate of change check. Let's update the plot here while waiting for the breaker to be reclosed. Okay, so now the breaker is reclosed again. The next scenario is on frequency disturbances within continuous operation region. Let's first set this switch to 0, and in this case we'll need a voltage disturbance as well. So we're going to set this to the third scenario and with voltage disturbance. And then the minimum frequency here we set to 58.8 Hertz. Okay. Now trigger the event by pressing the push button here. We can see the breaker is opened. Now in this case, the logic sets the voltage to 1.1 per unit, at the same time reduces the frequency to the target minimum value in the continuous operation region with the slope of 0.49 Hertz per second, which still satisfies the rate of change of frequency requirement. The trip we can see here is asserted when the V over F check is greater than 1.1 as expected. Okay, the last scenario for the demo today is rate of change of frequency read through. Okay, so firstly, we'll disable the voltage disturbance. Now here we're going to set the rate of change to a value that is going to be slightly bigger than the requirement. Okay, and let's trigger the event by pressing this button here. You can see the breaker is opened and then reclosed. So in this case, the trip was asserted as expected when the average rate of change of frequency, which is monitored here, is greater than 0.5 Hertz per second. Here. So that's when we tripped the breaker. Make it a better view here. So we can see here at this time instant, the rate of change of frequency is the average rate of change of frequency is is slightly over the limit, which is 0.5. At that instant, the trip logic worked, and then the breaker was opened after the drop-off delay. For RTDS users, you may access the full material in the RSCAD FX version 1.3 and above. Under the example cases, micrograde, small microgrades, and then you will see the series of examples here. So that brings us to the end of this presentation. Thank you for your attention. And now we are happy to address any questions you may have.
Hello, everyone. Hopefully you can hear me okay. Thank you so much for your attention during our DER interconnection webinar. and thank you for your questions. We did have a question about whether this is an available sample case, and Eric did a good job of showing you where exactly to find that in the RSCAD sample cases area. So if you have RSCAD FX 1.2 or newer, feel free to take a look at that case, run it, and if you have any questions on it, you can send us a support email, and Eric will help you out that way. We did have a question about the GT-SOC, about whether the .a file that I mentioned is proprietary. So I wanted to talk a little bit more about that. The best way to learn more about the GT-SOC is in our upcoming webinar that we'll have later this year. But essentially, the .a file itself is not proprietary. We have a tool that allows cross-compilation of the vendor's C code, or I believe Fortran code, to the .a file, and that's what allows it to run bare metal on the ARM core of the GT-SOC. But then a wrapper must be developed to exchange data between the real-time simulation and the control code. So that wrapper for data exchange is the more proprietary or application-specific process. It's basically the part that sits in RSCAD, the RSCAD component. And currently, each GT-SOC can run a maximum of 20 .a file instances, with each instance having 64 inputs and 64 outputs. So currently, those are the capabilities of the GT-SOC. But stay tuned for a webinar for more information. I think that is pretty much it for the questions that we had today. So with that, I just want to thank our audience, and thank you so much, Eric, for your presentation.
Yeah, you're welcome.
And we will see everyone at the next. Oh, before I forget, there is a couple of links in the handouts section in the bottom left to some upcoming training courses we have in person. So we have an introductory simulator training course and an advanced training course in renewable energy and microgrid applications. Those are taking place at our office in Winnipeg next month. So take a look if you're interested in some training, and you'll find more on our website. Eric, do you have anything else to add?
No, I just trying to type in the answer for Philip on whether we can offer a toolbox for implementing the grid support control functions. So basically, in this demo, all the control components are taken from our standard control libraries and also from protection controls specific libraries. So yeah, so they're all there. Now, in terms of a specific for there's not special made components specifically for this application. Yeah, so I hope that addresses the question there.
Yeah, thank you, Eric. Okay, yeah, that addresses Felipe's question. You're welcome, Felipe. And we have the slide link there for folks who want to download them. Any other questions, please feel free to contact us at support@rtds.com. Thanks, everyone, and we'll see you at our next webinar.
Thank you.